All right, let's just jump right in. We're going to tackle one of the most mind-bending and honestly most misunderstood experiments in all of physics, the delayed choice quantum eraser. It's this wild idea that seems to just rip up the most basic rule of reality, that cause comes before effect.
So the entire mystery really boils down to this one single question. Could a choice you make right now somehow ripple backward in time and change something that has already happened? I mean, our common sense, our gut, everything screams, no way. That's impossible.
And yet, this is where things start to get really strange. Because if you just look at the surface-level results of this experiment, it seems to shout back a baffling answer, yes. That apparent paradox, that seeming violation of reality, is exactly what we're going to unpack and ultimately solve.
Okay, so before we can even talk about erasing the past, we need to get a handle on the original puzzle. And it all goes back to the absolute cornerstone of quantum weirdness, the fact that tiny things, like photons of light, have a serious identity crisis. They act like both particles and waves.
This is the core of it all, the classic double-slit experiment. Picture firing single photons at a wall with two slits. If you put a little detector at the slits to watch which one the photon goes through, they behave like tiny baseballs. You get two simple bands on the screen behind it. Particle behavior, plain and simple. But, and this is the huge but, if you take the detectors away, if you don't look, something incredible happens. Each photon acts like a wave, going through both slits at the same time, interfering with itself, and creating this beautiful striped pattern on the screen. The very act of measuring changes reality. It's wild.
Now, this isn't just some weird quirk. It's a fundamental rule of the quantum game. It's a principle called complementarity. It basically says an object can show you its particle side or it can show you its wave side, but you can never ever see both at the same time. You have to choose which question you're asking, and that choice determines the answer you get.
So this leads to a really clever follow-up question. We know that getting that which way information, knowing which slit the photon went through, destroys the wave pattern. The system just kind of snaps into a boring classical state. So physicists wondered, what if we could get that information and then erase it? Could we bring the interference pattern back from the dead?
To test this, they built this incredibly ingenious contraption. Let's walk through it. First, it starts with a special crystal that creates a pair of entangled photons. Think of them as quantum twins. They're linked in this spooky way, so what happens to one is instantly correlated with the other, no matter how far apart they are. We'll call them the signal photon and the idler photon. Step 2. The signal photon flies off to the double-slit screen, just like in our first experiment. Step 3. Its twin, the idler, goes on a totally different journey, one that's designed to tell us which slit its signal twin went through. And here's the magic trick, Step 4. Right at the very end of the idler's path, a clever setup of beam splitters can either let us see that path information or it can totally scramble and erase it right before the idler hits a detector.
So far, so clever, right? But now we add the final ingredient, the twist that turns this whole thing into a brain melter, the delayed choice.
Okay, the sequence of events here is absolutely critical, so let's get it straight. First, our signal photon goes through the slits. Then, a moment later, it smacks into the main detector screen. Bam! Its journey is over. Its position is recorded and locked in. It's only after that has already happened that its entangled twin, the idler, finally reaches its own set of detectors. And it's at that later time that the experiment randomly decides whether to keep the which way information or to erase it. Think about that. The choice to erase is made after the event it's supposed to affect has already finished.
The great physicist John Archibald Wheeler, who came up with this idea, put the implications perfectly. He imagined doing this with light from a distant quasar billions of light years away. A choice we make here on Earth now could seemingly alter how that photon behaved when it left that star billions of years ago. I mean, that sounds like science fiction. It sounds like we're literally rewriting history.
So, is that what's happening? Are we actually breaking causality? Well, spoiler alert, no. But understanding why not is what reveals the true, subtle, and frankly much cooler nature of quantum mechanics. So let's solve this paradox.
Here it is. This is the single most important clue to cracking the whole case. If you just look at the main screen where all the signal photons land, and you look at all of them together, you see nothing, just a big, diffuse clump. There is no interference pattern here at all. At first glance, it looks like nothing weird happened.
But the pattern isn't gone. It's just hidden. And there's a fantastic analogy for this. Think of a digital billboard. If you turn on every single light bulb, what do you see? Just a bright,
featureless blob of light, right? The image isn't gone, it's just washed out. You can't see it until you start selectively filtering which bulbs you look at.
And that is exactly what's going on here. The pattern doesn't magically appear on the screen because of a choice made in the future. The pattern is revealed later when we go back through the data and sort it. We are not changing the past, we are simply filtering the present to find patterns that were there all along.
So how does this sorting work? It's all about the entanglement. We take our big, messy pile of data from the signal photons. Then, for each hit, we look at where its entangled twin landed. If the twin happened to land in one of the eraser detectors, we put its signal partner in one group. And when we look at just that group, boom, there it is, a perfect interference pattern. Now, if the twin landed in a which-way detector, we put its signal partner in a second group. That second group also has a pattern, but it's an anti-interference pattern. It's the exact opposite, a clump that perfectly fills in the gaps of the first pattern. When you lay them on top of each other, they cancel out, and you're back to the big, meaningless clump.
The absolute key is that you have to wait for the information from the idler photons before you can even know how to sort the signal photon data. You can't see the patterns in real time, so no information is being sent back in time. The past is safe. The scientific consensus is crystal clear. There is no retrocausality going on here.
So if this experiment isn't a time machine, why on earth is it so important? Well, because once you debunk the myth, you're forced to confront the real quantum mystery, which is arguably much, much weirder than time travel.
As Physics World puts it, this whole setup is a great thinking aid. It's not about changing the past. It's a tool, a kind of mental gymnasium that forces us to grapple with the truly bizarre, non-local nature of quantum reality. It sharpens our intuition about just how strange things really are.
And that weirdness cuts right to the heart of the biggest debate in physics. What even is reality? This experiment doesn't settle the debate, but it really highlights the stakes. Do you lean towards the Copenhagen interpretation, where reality is just a cloud of probabilities until we look? Or maybe the many worlds view, where every possibility actually happens, just in a different universe? Or do you think there are some hidden variables we just can't see yet? This experiment is a playground for testing these huge ideas.
You know, one of the biggest takeaways here has nothing to do with time at all. It's that the mere possibility of getting which-way information is enough to destroy the interference pattern, even if you never look at the idler photon. The fact that its path is entangled with the signal photon, that the information exists somewhere, causes the system to lose its quantum weirdness. This is called decoherence, and it's the #1 villain for anyone trying to build a quantum computer.
Ultimately, the delayed choice quantum eraser is a really humbling lesson. As physicist Sean Carroll says, it's a stark reminder that we shouldn't mistake our everyday common-sense world for the world as it truly is. Our reality of solid objects and linear time might just be an emergent illusion, built on a foundation that is profoundly stranger than we can imagine.
So, we end not with a solved myth about rewriting the past, but with a much deeper question about the present. This experiment confirms that the properties of a particle aren't set in stone until we measure them. The very questions we choose to ask of the universe help determine the answers we get. So, if our choice of measurement is fundamentally tangled up with the reality we observe, what does that really say about our place in the cosmos? That is the real mystery.